Thanks so much for joining. We're super excited to have you all here for this webinar to present the results of our California Energy Commission funded CO2 heat pump demonstration for large commercial buildings. We're going to be presenting our results from the project, a lot of the key impacts, and what's coming next. I'm Carolyn Wiseman. I'm a project manager at Prospect Silicon Valley, and I lead a lot of our technical products, including some of the industry resources that we're going to announce later in the presentation. But I think we have critical mass here, so I will get started with the agenda. So just highlight what we're going to go through today. We're going to start with a quick recap of the project and the technology. We will dive into the results of our demonstration, some of our key takeaways, and then we'll introduce our resources and training that are going to be available to the industry to support project teams that are looking to implement this technology in future projects or are just curious to learn more about it. And we're going to end with a discussion with our speakers about the impact and importance of the project for the industry and what they see as some of the biggest takeaways. We're also going to be taking questions from all of you at that time. So please feel free to put any questions throughout the presentation in the Q&A. And our team will be viewing those. And I see someone already put something in there. So yes, the presentation is going to be recorded and shared. And here are our amazing speakers for today. This is also our project team for the demonstration. So we have Adam Jue. He's project manager for Prospect Silicon Valley. I'm going to pass this over to him in a moment to tell you more about the project and what we've accomplished. And then we have Isaac Simpson, sales director for DMG North. DMG North's a leading HVAC rep in Northern California, and the distribution partner for Flow. And so for this project, they acquired, assembled, and delivered the heat pump system for the demonstration and are providing some workforce training at their decarbonization training center in San Jose, which they'll also be talking about later. And then we have Sean Jarvie, CTO, Flow Environmental Systems. Flow is a manufacturer of the Answer CO2 heat pump system that you're going to hear more about in a few slides. And then last but not least, we have Rongxin Yin, technology researcher from Lawrence Berkeley National Lab. LBNL is our measurement and verification partner, and they coordinated all the testing procedures at the FLEXLAB facility. Um, so Adam, I will pass it over to you.
Thanks, Carolyn. So yeah, I think it's important to provide the context first. I know we have some returning attendees from our previous webinars and then some new faces today. So I thought it'd be important to set the stage before we get started on the results. So California is at the forefront of reducing carbon emissions with a goal to cut emissions in residential and commercial buildings by 40% below 1990 levels by 2030. So how do we actually get there in the building sector? So I think it's important to start with, let's just start with the biggest elephant in the room. It's space and water heating. So together they account for 37% of energy use in commercial buildings, which is the single largest source of emissions attributed to these buildings. So to put that in perspective, large office buildings in California alone are responsible for about 10% of the state's gas usage and nearly 17% of the electricity consumption. So most of that gas comes from traditional boilers and furnaces located in buildings that haven't yet transitioned to heat pumps. And on the electric side, today's systems use a lot of electricity, which drives up operational costs and energy costs and puts pressure on the electrical grid. And to make matters worse, many existing HVAC systems rely on synthetic refrigerants with high global warming potentials. So now you might be thinking, but aren't there electric heat pumps already? I mean, yes, there are, but the rollout has been slow for this technology, for your conventional electric heat pumps due to various barriers. So next slide, Carolyn. So from a climate perspective, heat pumps typically struggle at very low or very high outdoor temperatures. In cold, humid conditions, they can accumulate frost, which triggers defrost cycles that temporarily reduce heating output and efficiency. And then from a technological perspective, most heat pumps can't reach the high water temperatures that condensing boilers can. So that can be a problem for existing piping, heating coils, radiators that were designed for high temperature systems. From an economic perspective, the numbers often really don't add up. The heat pumps generally have higher upfront costs compared to traditional HVAC systems. Retrofitting them can be very extensive, sometimes requiring extra space that buildings really just don't have. And then on top of that, they can increase electrical demand, sometimes, and then sometimes fail to fully meet thermal needs. And then finally, they can be really noisy. So now that we have laid out the challenges and the full context, I can turn it over to Sean Jarvie of Flow to talk about the flow system itself and the features that we tested for our demonstration.
Very good intro, and thank you. I'm Sean, and this is what we're talking about here, our flow answer CO2 heat pump. Next slide. So, as we're trying to meet all these demands and all these issues that Adam so poignantly laid out, the first thing is we got to have a toolbox of components to work with. So, under California law, we are on the GWP phase down. So, by 2025, 2030, 2033, and 2035, ultimately, we're aiming for a GWP of 10. If you look across HVAC and refrigeration industries, you don't really have a lot of great choices besides the naturals, and CO2 is one of those standout examples. That's what we've designed heat pump around. Next, please. In order to do this, we had to come up with a number of new innovations to make this happen. So we're going to see from Rongxin and results from FLEXLAB here coming up, a lot of how we manage load profiles, whether it's cooling only, heating only, or simultaneous heating and cooling, without a reversing valve and the complications of shutting that down, turning it back on, and doing really wildly unbalanced loads for the building's actual environments and maximizing that effectiveness. It has to work in all climate zones. It has to deliver high temperature so that we can do heating replacements, but also we have to have high return water temperatures that are essential to control like you would control a typical hydronic system. And then a big thing that does struggle a lot of systems is the defrost, and we have a way to mitigate all that defrost with this type of technology. Next, please. So what does this look like? Well, we've developed this into an air to water or water to water system where it's optimized as either a standalone water to water system, say geothermal, or packaged heat recovery, or you can do with the air source as well, either a split or packaged. And so you can mix and match your source in your sink. Next. So with that, we have a number of varieties and Lego bricks to go with it. Essentially, you got a 20-ton system that we spent a lot of time on, and you'll see pictures of and photos shortly. It fits through a normal commercial door. It goes up and down freight elevators, and it's modular. Then we can step up to the larger sizes for the larger buildings, the large commercial appliances that we're talking about now, as well as the options for air source and water source. Next. So when we look at a system like this, have to ask ourselves a number of questions, whether air or water source. You can see here, we can go from -40 all the way up to 120 outdoor ambience, but also we can now put the loads together in true simultaneous forms. We can do them individually or together. So if you get high grade heat, your boiler replacements, your low grade heat, your domestic water, your hydronic heating loops, your chiller loads, as well as any kind of low temperature or dehumidification loads you might have. So you can see here that now all these systems can be combined into one central plant in a box so that we can do modeling and projections for these buildings. And we're doing it today across the state. Next. And then I like to show this as we'll talk about it more, but legacy systems, we got chillers, we got boilers, we got furnaces. So as we've been on this electrification journey, we end up doing modular heat pumps. We end up dealing with extra heat pumps for the defrost. They start taking a lot of space. We can't go hot enough. All the things that Adam mentioned early on. And that makes heat pump deployments expensive and complicated to roll out. With a system like this, we can eliminate that defrost, eliminate that extra booster heat pump or electric boiler. We can combine multiple loads into one. So you got chillers, boilers, and domestic water in one unit. That typically saves space and allows for a parallel scale deployments, which makes all of our financial people happy. On top of that, we can go no new power feeds and um, really make it a system that fits the existing footprints of buildings. Next.
So to lay out the foundation of our demonstration, which was funded by the California Energy Commission. We had two major goals. So it's one was to demonstrate a fully functional heat pump with various conditions, including heating, cooling, domestic hot water, and simultaneously doing all those functions with a system that's 100% electric and with a really low GWP. And then secondly, it's to demonstrate the benefits to end users, including lower cost of ownership, just human and building comfort in general, and environmental stewardship and energy efficiency. So, as mentioned before, the site location of this, the demonstration took place at the FLEXLAB facility, which is located on Lawrence Berkeley National Lab's campus. FLEXLAB is actually the first facility in the world capable of evaluating the energy performance of major building systems as a fully integrated system under real-world conditions. So what makes it so powerful is that these test beds can monitor and assess everything, not everything, but a lot of things from HVAC systems and lighting to windows to control systems, building envelope and plug loads, all in any combination. So that's really cool. The testing period for the flow system at FlexLab took place between March 31st and June 13th of last year, or what I like to call late winter, early summer testing. Some of the data that we collected also that factored into evaluating the performance of the system includes indoor temperature, humidity, airflow rate, water flow rate, power consumption, refrigerant data, and outdoor weather. So all these variables contributed to measuring the efficiency and demand flexibility of the flow system. More of which you'll hear on later. So you'll see this in a later slide also, but we went all out. We even had thermal mannequins mimicking the temperature of the human body. So, like I said, we went all out in simulating the full, large commercial building, large office experience. And finally, we'll dive into this later, but it was extremely important that this project reach the right audience with the right resources and information. So extensive outreach was conducted from providing industry resources, opening a full-on training center in San Jose, thanks to DMG, presenting at conferences, and providing site tours of the demonstration site while the demonstration was going on. So yeah, I'll leave it up to Rongxin to provide more context on the results that actually happened.
All right, thanks, Adam. Thanks, Adam and Sean, to recap the project. And regarding this project, and I'm pretty sure everyone can see my background, which is our FLEXLAB. And so for this project, I will use the FLEXLAB to demonstrate the solutions we propose in this project, which is to demonstrate Flow's CO2 heat pump in place of existing uh, heating and cooling plants. So the baseline, which is clearly three independent systems, chiller, boiler, and domestic hot water plant. So the point made here is no thermal sharing built-in system. It's just for the supply side point of view. It's not on demand side. I'm pretty sure there's some open space. They have simultaneous heating and cooling load, but here just talking about from supply side. And so the Flow's answer to the heat pumps is capable of providing chilled water, hot water, and high-grade domestic hot water up to 180 degrees simultaneously, and from one and only energy source, which is electricity. And that makes 100% electrifications of the HVAC systems. And in addition to the end performance testing at FlexLab, we also observe the unique design on the gas cooler system, which has advanced defrost design, and the heat pump has the built-in controller that capable of doing the grid interactive control and for the load flexibility testing as well as grid resilience come along with energy storage component. And you can see the diagram here. And so basically, in the winter period, we have the heating load on the parameter zones, and we have all year round cooling need in the interior zones, and we have surface areas in the buildings that need the domestic hot water usage. So that's drive us use one unit to meet all the space heating, cooling, and hot water usage at the same time. So this is the solutions we can demonstrate. And let's move on to the next slide. All right. So as you can see the pictures on the right side, and the unit is pre-assembled and mounted on the trailer from the uh, flows, facility in Minnesota and shipped over to a lab. Luckily, I mean, we are glad to see the unit come to lab as one piece. And so through installation, we did have the like minor issue during the installation process. There's a loose joint connection to the water storage tank. This is that first day we put the water go through the installation and testing phase, and we just fix it. So I think this is one issue we deal with, but it's just minor. And you can see the diagrams on the left side. The FLEXLAB, which is we call FLEXLAB, which means it's flexible for all type of reconfigurations. And the existing the test bed has two identical cells, and this test bed is served by one air-cooled chiller and a natural gas boiler. Um, and in the hydraulic systems, there are a few connection points that allow us to bypass the existing chiller and boiler plant, and very easy for us to connect the unit to the existing hydronic systems. You can consider it just very easy to plug and play the systems and integrate with our test bed. And for the unit, it has six pipes, two for each of the space heating, and to the each for the chilled water loop, hot water loop, and the domestic hot water to the testing rig in our separate test cell. And as Adam introduced, for each room we have two phases of testing. For phase one, we have the winter testing, and we configure the test bed to be, air handling unit plus the VAV terminals for each zone. And the reason why we put the fan coil unit here, since like the existing reheat using the electric. And to make use of the hot water from the unit, we reconfigure, we disable the existing electric reheat, resistance, and using the fan coil unit for the reheat. And for some testing, we just configure as a DOS plus the fan coil unit for some testing. And let's move on to next slide. All right. So I'm not going to cover, the details of how we, our testing, but this is overall demonstration project, results from our phase one, phase two testing. And you can tell there's some constraints with our test bed, set, for the heat pump testing, because the test bed is about 1,200 square feet, and during the testing period in the winter time, the max heating and cooling load is up to 3 to 5 tons, which is about like 30 to 40% of the capacity of the unit. And the unit we have, which is 20 tons unit, even though we disable one of the compressors, but still it's like oversized for our test bed. But even though you can tell for the individual mode cooling only, the CO2 range between 2 and 4, and the average, the cooling COP is about 2.8. And for the cooling only operation mode, we have range between 1.6 to 2.7, and the mean, which is 2.0 for the heating COP efficiency. And we have very good performance for the domestic hot water because there are large RT between supply and we have supply 140 and returns 50. And although we test a few days that supply up to 160 and a few hours to 180, but just for the capability testing for the how much, how high of the temperature we can goes up for the domestic hot water. And the COP range between 2 to 4.2, and the mean COP for the domestic hot water only, which is 3.1 roughly. And regarding the combination mode, which is as just mentioned in the first slide, so when the unit providing chilled water, hot water, or even domestic hot water at the same time, the combination mode COP is it's pretty nice because we resolve all the heat release from the cooling cycles. And the COP range between 3.0 to 6.5, and the mean COP up to 4.5. This is overall COP performance of the unit in individual mode and the combination mode that runs cooling heating simultaneously. And because of the oversize the plant, we just test up to 6% of the overall load conditions. And we do have some mental data and some mental testing in the manufacturers' facilities. That the data site we just combine with our laboratory testing data to fit performance curves. I'm going to describe that information later on. In addition to the end performance of the unit, we also conduct a few weeks about demand flexibility testing. Uh, you know, um, just implement common use global temperature adjustment to see how the system and plant respond to those set point adjustment, and just few just key metrics about load shed and load take. Um, so consider the load shed during the on-peak period, and the load can reduce zero point 0.5 to 1.0 watt per square feet. And if you have like we do have a storage tank, but things like if you know um like say lower the set point during the daytime, which is kind of like part load, part mid peak, and the load take metrics roughly between 1.3 to 2.3 watt per square feet. And the heat pump is capable doing up and down of the load flexibilities compared to the traditional as cold chiller, either like natural gas boiler. You barely can do nothing for the heating seasons load flexibility. And let's move on to the next slide. All right, so this is a supplemental slide about combination mode system performance. As we can see, when the systems at well-balanced load conditions, the average COP can range around like 5.5, and from 4.3 up to 6.5 with a well-balanced load. And if either the system running the unit running the cooling dominant or heating dominant, there's unbalanced load conditions. The COP average COP range between 4.3 up to 4.5 of the overall unit performance. And let's move on next slide. Just very quick recap of our demand flexibility testing, and we only implement the global temperature adjustment DF measure in our test bed for the pre-cooling during the on-peak period. No, sorry, pre-cooling during the mid-peak period from 12 to 4 o'clock, and between 4 to 9 o'clock, we just raise the set point by 4 degrees, and this is power response on the system side, and roughly we got 10 to 16% of the load reduction during the on-peak period. It's just for the temperature adjustment testing measure. We haven't incorporated any storage, thermal storage in this demand flexibility testing. Next slide. I think I already walked through the constraints that we have during testing, which is oversized capacity for the small areas flow FLEXLAB test bed, and the we originally we think we want to use the cold storage, the water tank for the storage testing, but eventually just operate as a buffer tank rather than the summer storage.
And
So
Rongxin,
let's.
while we're on demonstration constraints, we got a question from Stephen Getman in the Q&A asking the extremes of outdoor air temperatures during the testing. Do you
Oh, I mean, in the winter testing period, we do have a week of outdoor temperature get down to 45 to 50-ish. That's the coldest week we got during the testing. And we run the domestic hot water operations during the night hours, which is like 45 to 50 uh, degrees.
and on the other side we got up to
We got up to the 80 degrees for
yeah.
the summer week, no, which is hot week in the winter period. Berkeley weather is kind of like few weeks cold, few weeks like warm, and get up to 80 degrees.
Yeah.
All right, I think I'm on the 10 mark. Let's walk through the final slide I have. And so based on data we collected from laboratory testing, and also we have supplemental data set from the Minnesota testing facility. So we consolidate all the data to fit performance curves for the CO2 heat pump. And we leverage the prototype building models and the modified model to be, roughly about 200,000 square feet, large office building, and ran the model in four climate zones in California: Sacramento, San Francisco, Los Angeles, and San Diego. And you can tell the main difference between these four climate, which is the heating load and cooling load, breakdown, ratio of the overall sum load. So that's why, we have like huge improvement of COP in Sacramento and San Francisco area because of there's more operation hours for simultaneous heating and cooling. But in Southern California, Los Angeles and San Diego, which is cooling dominant, and that's we have less hours of the combination mode of the heat pump unit. But still, because of like the during the winter season, if you run the unit at simultaneous heating cooling mode, that drives high performance of the unit get up to the improved COP compared to the air cooled chiller plus natural gas boiler as a baseline. And which means simultaneous mode matters. That is the main driver I want to point out here. I think that's I can go through. All right, Adam, back to you.
Thanks. So Rongxin, yeah, gave a great overview of the model results across different climate zones. But a question that everyone, especially building owners, eventually asks is, what does it look financially? So to answer that, Prospect SV took the same use cases from remodeling and conducted what's called a net present value or NPV cost analysis. So essentially, we looked at the total cost of three different HVAC systems over time and converted those costs into today's dollars so that we can compare them on a level playing field. The three systems that we analyzed were, of course, flow CO2 heat pump, then a conventional modular slash split heat pump, and then finally a gas boiler paired with an air source chiller. So the latter two of which you could conventionally see in a large commercial building. Now, I want to emphasize that this analysis is based on public data sources, industry averages, and discussions with experts. So this isn't meant to represent a specific project. It's more intended as a high-level cost estimate for large commercial buildings. And what we found over a 20-year system lifespan is that Flow's system shows a lower overall net cost across every climate zone that we evaluated. And that advantage is driven largely by operating costs. So as presented, which is presented in light blue in the graph. So those things include things like maintenance, refrigerant replacement, and the energy required to run the system and the costs associated with that. So because Flow system has a higher COP based on the modeling, it consumes less energy. And that translates directly into lower energy costs over time. And then also, there's also the refrigerant factor. CO2 is significantly cheaper than the synthetic refrigerants used in many existing systems, which further reduces long-term costs. So if you're interested in digging deeper into the details, the full analysis, includes our methods and assumptions, it's available on our website. So that's really the high level financial picture of it. But beyond cost, another key question is how these systems actually operate in real buildings. So Isaac, I'll pull you in, Isaac from DMG, to walk us through maybe the practical day-to-day effect, benefits of this technology compared to maybe conventional systems on the market today.
And
Hey,
just
Adam.
a quick note on here before we move on. This was covered in our modeling results, but the building size and type that we're using here is a 175 to 200,000 square foot building, depending on the climate zone. And this is for a large commercial office.
Yeah.
So
Thanks, Carolyn. Thanks for that clarification.
no problem.
Great. Well, Adam and everybody, thank you. Yeah, I think that cost is very important, and I think that previous slide really talks about just the operating cost of a flow system that is capable of doing all the heating, cooling, and domestic hot water needs for a building. But when it gets to what else is the owner going to experience with a heat pump? It's one of the things that prior to this system coming onto the market, if we were looking at a heat pump, one of the big things that we would have to deal with is defrost. So a certain number of hours of operation, whenever we're in heating, the system would naturally build ice on its outdoor coil and then have to stop operation and operate in a cooling mode to heat up that outdoor coil and de-ice the condenser coil, the outdoor coil, and then stop operating again and go back into a heating mode. So there's a significant period of time out of each hour. Maybe it's 8 minutes, 10 minutes, 15 minutes, depending on the system type, depending on how the coil circuiting is, that the heat pump is not doing its job, which is heating the building. And so there's a couple things that come from that. One, you have an energy penalty. You're stopping the heating that's going into the building while you're running it and cooling. You're not getting the heat into the building, and there's an energy cost to de-icing or defrosting the coil. You have to make that up somehow. You have to either have another source of heat, you have to have another heat pump, you have to have a larger system, or you have to have some backup heat, which often has been done with resistance heat, which is a very low COP of 1.0. So you're either using some resistive heat, some backup boiler, or you're paying for a lot more heat pump. So for one of the biggest benefits of a flow system is by never going into defrost, by not having that reversing valve inside this heat pump system, you're not going into that defrost mode and spending that extra energy. So right there, that's a big win. You're also not, depending on where that heat pump's located, de-icing the coil and putting a lot of water onto, say, a sidewalk that then gets icy or something like that. So right away, defrost is a big one. Now with the testing at FLEXLAB, you're getting proven performance. We know exactly how these things are going to work between the FLEXLAB data here in Berkeley, the Minnesota testing facility that added data to our overall study. We've got proven performance. All of these systems come with an intense diagnostic monitoring system that looks at all the temperatures, pressures, and operating points of the system so that we know exactly the health of the system and how it's supposed to be working at all times. That's kind of a peace of mind or assurance that not only has this been proven to work, but we're constantly going to monitor it while it's at that building delivering heating, cooling, and hot water. And really, one of the cool things is when you dig inside the flow system, this is an industrial quality, industrial level product that has been taken out of that space and introduced to the commercial space. So it's just a extremely rugged, well-proven set of compressors and components that are now able to do commercial heating and air. You're just going to get a longer life out of that type of system. Next slide, please. And then if you're considering bringing this into your existing building, one of the biggest advantages of having this mechanical room in a box that does heating, cooling, and domestic hot water in one is just the simplification of tying that into the building systems. We proved that at FLEXLAB with just how easy it was to roll the trailer up to the site and and plug it in, essentially just hook up some hoses and power, and we were off to the races. And that was quite exciting for the team. But here, when we're talking about replacing potentially like a boiler and an air-cooled chiller, we're not having to resize every pump, every pipe, every coil that exists inside that building because we can operate at temperatures that a conventional heat pump would not be able to do. I think we have Carolyn, if you could help me, or there was a question in the chat that do we have a question in the chat for this section? I'm sorry.
Let me see. I'm looking at the Q&A. Are you looking in the
Oh,
webinar chat or the Q&A?
the Q&A or the webinar chat. I'm sorry.
Oh, we
I
had someone
think.
with their hand raised, which
Oh,
we can
okay,
take
great.
people with their hand raised at the end, or you can put your questions in the Q&A chat. But I think just you can
Perfect.
continue, Isaac, and we can
Well,
address them.
yeah, so just quickly from an owner standpoint, if you're looking to retrofit and considering the heat pump technology from Flow, what you have is essentially that you have a simplified system, basically everything in the one box, and that you're not having to go through your entire building and change all the rest of your hydronic components in order to apply this system to that building. And if we look at the other technology that's out there, that usually is a stopping point for feasibility of one of these upgrades.
All right, Adam,
Thanks,
back to
Isaac.
you.
So yeah, presenting these results and benefits to all of you is extremely important, and that's why we're all here today. But the reality is, there's a lot more that goes into evaluating whether this technology actually makes sense for a project we're building, and that's why we're really excited to announce something that Prospect SV has been wanting to develop for a really long time. Something that building owners, designers, MEP firms, contractors, operators. They can all use to streamline the process of evaluating CO2 heat pumps in their projects. So that resource is our new industry guidance package for CO2 heat pumps in large commercial buildings. So, and because you are a part of this webinar today, you will get early access to this webpage, which you can find in the resources section of the Prospect SV website. You can also scan the QR code on this slide. So this package brings together a wide range of materials that support both the pre-design evaluation process and just broader education for the building industry around CO2 heat pumps. So inside this package, you'll find things like a technical data sheet of the flow model, a BIM object for designers to use on Revit, a deeper breakdown of the model performance that Rongxin mentioned, summaries of key benefits and challenges of CO2 heat pumps. There's also a funding and incentives guide, and then opportunities that you can look through if you're looking to fund or finance your project. And of course, the NPV cost analysis we showed earlier, just in greater detail. So according to the very, very formal and highly peer-reviewed meme on the right of this slide, by attending this webinar, you've already reached almost full enlightenment. But if you want to reach peak omniscience, you can scan the QR code to explore the rest of our resources, things like talking points and additional communications tools. So, but in all seriousness, I highlighted this portion because the talking points portion, because it's critical that everyone involved in a project implementing this technology kind of understands what's in it for them. The resource not only gives each collaborator the chance to learn about the technology, but they also provide insight into what other industry experts or stakeholders might find important. And that helps bridge the communication gap between different stakeholders on a project. So I've already said too much. You just need to check it out for yourselves. And of course, we're always happy to connect outside of this webinar if you'd like to talk more about these resources or how they might apply to your projects.
And then I think we're going back to Isaac to talk a
Yeah,
little bit about DMG's training center.
thanks, Em. So, one of the really exciting parts about working with the team on this project has been building out the San Jose Training Lab, which has a working system, the flow answer heat pump, the same model that was featured at the FLEXLAB during training, and you could see here in the photo with some of our team members. This installation is for ongoing training of the entire industry. We are bringing in owners, developers, industry thought leaders. We're bringing in the mechanics, the service tradespeople that will be working on these systems on the refrigeration side, on the piping and hydronic side, the plumbing, as well as the sheet metal, and exposing them to a new technology. And this is just a part of what that picture shows is the actual heat pump in a split arrangement. You can see the compressor section right behind Doug Davenport, and then the uh, gas cooler section, a little bit of it there in the foreground. Way in the background, you see a TV monitor that's showing the real-time operation of that site. And if we go to the next slide, we can talk a little bit more about that space, which is in the top left, the pumping and buffer tanks that connect into the heat pump. So that's managing the hot water and chilled water going throughout the space. And then we can do things with our setup to simulate additional load beyond what the space would have, just the ambient air temperature. And then inside, also the next picture on the top, kind of more in the center, we have taken and modified a shipping container to install a number of different fan coil units that would be used in everything from a commercial office space to a K-12 site, a hotel, or senior living. We really did go out and just look for a variety of different terminal units that it would be used in all types of applications to be able to pipe those in and operate them in heating or cooling mode. We can operate any number of the fan coils, all in heating, all in cooling, or mixed mode, just to show off the capabilities of the heat pump system that they're attached to. So that gives us a lab that can create a lot of different simulations, situations, and really let people who are interested in this technology come and see it and get hands-on with it and understand that it really does work. I think in some of the different tours up at the Flex Lab, and now over the last 6 months bringing people into the San Jose Training Center, when you first describe this technology to a lot of people, it kind of hurts their head because it sounds like something that's not quite possible. And one of the phrases that had come up during that period was, by bringing them in and showing them a real working system, it's their chance to come and pet the unicorn. That thing that they didn't think could exist is now real. It operates. It does what we say it's going to do, and they can come in and see that hands-on. So we're excited to continuously bring small groups through, private groups through, or attend our regularly scheduled trainings. Could you go to the next slide, please? So here's one of those classes happening. They're available on our calendar. That's something that Prospect, you go to their website, they'll publish. It's also available on the DMG website. But that at least monthly, we hold public training courses. We've scheduled a number of private events for different industry groups, utilities, and other industry parties that just would like to come and take a look at the system, and we're happy to schedule those times and have the right technical resources available for you for your visit. And that's all.
Awesome. Over to you, Sean.
Yeah, so this is all well and good. Let's talk about how to put it in other places. So there's a lot of different varieties of building types, and every building type is a little bit different. Um, whether you're dealing with a multifamily, institutional, industrial office, pharma, lab, hospitals, you name it, there is something unique about it. But when you have a system that is capable of doing a very wide range of hydronic hot water and chilled water temperatures with a variable source, whether that's air source, geothermal, or heat recovery from the building itself, you can make these work. So Adam's going to jump into a multifamily example here. But as before we get to that, there's a number of institutions deploying this right now, um, from university and corporate campuses to industrial process jobs to large commercial office spaces that Rongxin had modeled for all of you earlier and showing you what a 200,000 square foot building may look like to corporate headquarters, hospitals, schools, hospitalities, hotels. The opportunities are very vast when you have a system like this. On to you, Ed.
Thanks, Sean. Yeah, so like Sean said, we're actually gearing up for another CO2 heat pump demonstration. So we're really excited to announce that Prospect SV will continuing to work on this type of project alongside my fellow panelists here by demonstrating Flow's CO2 heat pump on a multifamily housing site based on 34th and San Pablo Avenue in Oakland, California. So there was a question earlier asking for relevance of a 50,000 square foot building. So this site is a 64,000 square foot building. So it will be more applicable to that uh, relevant square foot building right there, and more, it will provide more of a valuable context for those kind of like those mid-sized buildings. So what we'll be doing here is developing a nominal 10-ton heat pump with a single compressor for residential space conditioning and domestic hot water, running vigorous laboratory testing to verify its performance. We will then develop a similar heat pump that will be demonstrated at the multifamily residence on 34th and San Pablo for 12 months. So running and the system will run alongside the apartment's own system, giving us a really a true comparison with conventional heat pump, HVAC, and then water heating solutions. So in this manner, we are taking robust steps to ensuring we encompass all aspects that go into demonstrating this technology in a multi-family setting. So we're super excited to continue verifying and expanding this technology to multiple applications. So stay connected with us for more info as the project progresses. And big thanks to the CEC for giving us this opportunity, and a big shout out to our partners for this project, many of the logos of which you can see below on this slide. So, Carolyn, next slide, please. So, along with future projects that ProspectSV will be involved in, there are more exciting reasons to stay connected with us. We, of course, have our new industry guidance package for CO2 heat pumps in large commercial buildings, which I mentioned earlier, and you can access again via the QR code that we've had again in this slide here. ProspectSV will also be involved in more events during SF Climate Week, which will be running from April 18th to the 26th, that's basically a week chock full of events that are meant to exchange ideas and connect others to foster climate solutions. And also, Prospect will be organizing another event in San Francisco that I think a lot of people will be really, really excited about. So sign up for our newsletter via the QR code on the bottom right to stay up to date. So that's what we have on our formal presentation, but don't go anywhere because I think it's really important next to discuss kind of the impact and relevance of this project to the wider industry.
Sweet. Thank you, Adam. I'm gonna stop sharing so we can get our beautiful faces up here. So thank you to the team for those great presentations. I know we just went over a lot of information and a lot of results, so we wanted to take a step back for a little bit and talk about the broader impact of this project for the industry. I know this is the first US demonstration of Flow's answer system. We went through quite a few key takeaways and some of the key benefits that we demonstrated through our testing program at FLEXLAB. But I kind of wanted to pose to our speakers, reflecting on this effort as a whole, could you each talk about what some of the biggest implications or opportunities are for utilizing this technology in commercial buildings that either may have not been obvious from the results or that you would want to just drive home? Maybe something that we've already talked about, but is really key for everyone here to take away. Do you
I
want us to
can
go in any
start.
particular order? Thanks,
No,
Adam.
I can start. By I think by zooming out and kind of ask, what did we really demonstrate here? Yes, we showed the efficiency is important. But I feel like the bigger takeaway is that when you see it in a broader picture, with CO2 heat pumps, especially with capabilities like simultaneous heating and cooling and integrated hot water, you're starting to see a system that can, dynamically respond to building loads and even, external grid signals with demand flexibility. So, it's not just about efficiency, which is really important. It's about enabling more flexible, integrated grid responsive buildings, and that has a downstream impact on everything that, from how we design systems, and then from how we size electrical infrastructure, to even how buildings participate in demand management, and then within all of that, that broader context of, how of our broader decarbonization efforts for buildings.
Awesome. Thanks, Adam.
I can add one more to that. One thing that was not mentioned here that we spent a lot of time on is our technical advisory board. And we had a large coalition of a lot of the engineers and stakeholders and people who design buildings and run buildings participate in this project, and we talked about it. And when we finally showed the unbalanced versus moderately balanced versus severely balanced, as Rongxin like to call it, where the loads are all over the place and the heat pump's just chugging along and everybody's happy. That's not a traditional thing you see, and it doesn't really come across in the data. But when you see a highly unbalanced load and it just absorbs all the transients that you can throw at it versus traditional heat pumps would fail. One of our TAC members was really excited. He's like, this solves so many issues. And that was just a really fun day when that happened.
All right, so I can add 2 points from my, you know, perspective, since I have gone through the entire project process, and the feature like which is the plug and play, and as well as the integration of the unit to existing systems. Um, and especially for the integration, because the controller built on the unit has an open, standard protocol, either backlight and through the Modbus connection, and which is very easy for us to integrate into our existing BMS systems for all the data connection as well as the monitoring and the control, all these work. And second point, as Sean mentioned, so we are looking forward to the uh, expansion or either further step of the use of the unit, because we see, it's like if the unit run either cooling only or heating only mode, there's not much difference from the traditional, air cooled chiller and heat pumps. But things like because it's CO2 driven and it can still, perform well in extremely cold, wet conditions. But the reverse side, but things like we see the high performance during the simultaneous mode. That trigger questions like how we can push the unit run at the simultaneous mode. Okay, just add on some, some storage or phase changing material modules along with the unit, and use that, storage to manage the unit run simultaneous mode most of the time as much as possible, and also to avoid additional uh, you know, demand charge, that because we electrified these heating systems, that we have the impact to our peak demand. So I think this is another point I want to make. Lesson learned from this project.
I think one thing I would add from where we should be looking to apply these systems, I think first and foremost, existing commercial buildings who are typically running a boiler today, the heat output, just the temperature output of this heat pump chiller, being able to do 180-degree leaving water temp, and even if we don't run our building at 180, we might run it at 170, 165, something like that. The ability to go into an existing building with air handlers or VAV terminals with single row reheat coils and be able to utilize that piping and pumping and infrastructure because of the temperature that it can deliver. I just wanted to be clear, that's the key difference of being able to retrofit. We're not designing new buildings around those temperatures, but we have I don't even know how many millions of existing square feet of existing building stock that has that piping and those coils designed for those higher temperatures that these conventional heat pumps just do not deliver. And even if they could do that with a booster system, it would not be done efficiently. So if we can find, and it just the feasibility of retrofitting so many existing buildings that today are heated with boilers is really the exciting. I think the low hanging fruit, if there is such a thing, in decarbonization, and doing it on a wide scale.
Yeah, thanks, Isaac, and thanks, team. This is kind of a similar question, but I kind of wanted to focus in on for the engineers and architects, so like the people that will be designing these systems in future projects. Is there anything that you would add or highlight that you think is critical that may influence their work or how they view this technology when it comes to actually designing this system? And I think Isaac, you kind of just talked about that in terms of retrofitting, but wanted to
Well,
bring that up in case anyone had any other points.
I'll add one thing to that, which is, and I would hope the other panel could help me, right sizing. Um, our existing heating systems are massively oversized, comically oversized, maybe. Um, right sizing the heating system. I'm in charge of sales, and I'm telling you right now that I don't want to sell you more than what you need. We need to sell you the right size piece of equipment for your application, and both Rancha and Sean could certainly help highlight some of the massive difference between what's needed in a building and what they might currently have.
Yeah, I would add to that. I mean, the old rule of thumb used to be you picked your largest load on a peak design day for 5 or 10 years, and then you put a safety factor on it. Then you doubled it because you wanted redundancy, and then you round up to the next size. So you're almost guaranteed to be comically oversized, as Isaac said, on heat. But the other thing you got to really think about as you right size, which Rongxin's energy models really show well, and when he does the 8760 models, is that you don't need all that for most of the time. And if you added a little bit of thermal storage to your load, then all of that can be downsized so you have the best cost-effective system possible. And then one other thing I would add to that is think about the dollar per square foot of the building, not necessarily the dollar per ton of equipment or dollar per BTU of equipment, because now you are combining systems into one. So you're designing a mechanical room, not necessarily a singular piece of equipment, because we're putting domestic boilers and chillers all together. And that really makes it pop for the effectiveness and the affordability of these systems.
Rongxin, if you didn't have anything more to add, I was going to pivot to something related to costs, but something that just was another key takeaway for the design of the system and thinking about it is kind of thinking about the refrigerant subject kind of differently. It's not just kind of like a technical feature of it. It's, I think what this demonstration showed is that, CO2 isn't just a low carbon option. It's also, inherently safe and like and cost effective over the long term. So, it's non-toxic, it's not flammable, which is especially important in large commercial buildings where you're going to have hundreds, if not thousands, of people in one central place. When you look at our NPV analysis on our website, you will see that, over a 20-year lifespan, the lower refrigerant costs actually is one of the driving factors in reducing overall operating costs. And not to mention the regulations. The regulations are here the phase out is coming. And so now it's about preparing now for it so that by 2033 or 2035, you're already equipped to scale the adoption of CO2-based technology. So I guess the takeaway there is, CO2 heat pumps aren't just viable, but they can change the way how you approach system design from, a safety standpoint and a future-looking standpoint too.
I think I don't have other, add-on, but I just need to point out, during the laboratory testing, we do have a lot of visitors coming on site and check out, it's like what's the CO2 refrigerant compared against the traditional, the chillers using the R41A. And I need to point out things like if you consider the refrigerant leakage from traditional, chillers, definitely, and it saves a lot given the current like 10 to 15% of the leakage rate for the old chillers, and that's give you other like benefit uh in regarding the natural refrigerant used in the heat pump unit.
Yeah, thanks so much, Rongxin.
Mhm.
Yeah, and on the topic of our tours and having people come on site to see it, I think we had something like 100 plus folks come and view the unit. So that was a really great opportunity for everyone to see it and ask questions and experience how quiet it is um, in real time. And I wanted to bring up a few questions from the Q&A. I know we have plenty of time to go over these, so I would encourage people to continue throwing their questions in here. But we had a few specific ones about um, CO2 as a refrigerant. We got a few about the operating pressure of the CO2 heat pumps. So maybe Sean, you can touch on that.
Yeah, so the heat pumps with CO2, there's been this narrative that's been told that it's unsafe, it's high pressure, it'll blow up on you or something like that. Well, that's just simply not true. It is a higher pressure refrigerant. It can operate much higher than others. So our low side averages between 200 to about 650, 700 psi, depending on what mode we're in. And then the high side averages between 700 and about 1500 psi. That allows for us to operate in all the conditions we need to. That may sound high, but we're using Schedule 10 stainless steel and all that, which has a working pressure much, much higher than what we need. And CO2 is a lot more volumetrically dense, meaning we can scale our line sizes down. So they're much smaller line sizes than a traditional system, as well as much safer and more robust and more hard piping and tubing, to Isaac's earlier point, built to more of an industrial standard than a value engineered solution that others might be pushing. And one more comment on that. A few things popped up on affordability of the refrigerant. $1 or $2 a pound versus $10 to $30 a pound for the wholesaler cost. Installed cost is orders of magnitude less for vendors, and because it's not a proprietary refrigerant. It is a class A1 refrigerant, so it's safe, non-toxic, non-flammable, so it can go into your buildings. You don't have to worry about your A2L or A3 requirements. And then add in the fact that the charge concentration limits are very different here. So typical A2Ls are 2 to 4 parts per million, where now we're talking 5,000 parts per million for CO2. So very, very different expectations of what you need to do. There's projects that have happened just on that aspect alone.
Right. And Sean, you mentioned piping. We had a question in the Q&A. What sort of piping and pipe connection would be required for the refrigerant line running between the indoor and outdoor components for the split configuration?
Yeah, depends on the size, but we usually recommend a Schedule 10 304L stainless steel material. Match the connection sizes that are in the IOM or the submittal for your project. And they can either be orbital welded or TIG welded together, or else there is a copper brazing option that's out there with a type K65 or an iron impregnated copper. So you can use a variety of those. That stuff's pretty expensive these days, so we usually recommend just stainless steel tubing between the two. And they go together really quick.
Awesome, thanks. And I would also encourage, I know we have some some pretty specific questions in here, and we would love to set up some chats outside of this webinar if you have some detailed questions like that. So yeah, our team is available to chat with you, and we would really welcome that. So we can follow up after, or we have our contact information that's been in the slides, and we'll send an email out after. So please don't hesitate to reach out and set up a chat.
Oh, actually, Karen. Sean, would you like to answer a question about open, the operating pressures of the CO2 on the high side, side temperature? I think remember it's like 12,000 in 1200 and 1400 PSI. I'm
Yeah,
guessing,
I
right?
answered in the chat already,
Oh,
but yeah,
okay.
maximum is 1500 for
Yeah,
operating
1500.
loads.
Yeah. Otherwise, see.
But typically it operates much less at lower conditions. You only need that for the very high temperature applications.
Cool.
Awesome. Thank you.
There was a comment of 175 typical for PSI. That is for a low pressure refrigerant like a 134A, which are out on GWPs. 513A would be the last one that's going to be available on phase out. But now we're jumping up to some of the A2Ls and different varieties that have other requirements.
Awesome. And then there's a question in here, are there space limitations to installing these units? And if so, what are they?
We've designed the systems so that they are minimal space require. So we've designed everything for a 42-inch clearance for NEC electrical codes as our primary driver. That includes our gas coolers instead of a condenser, and allow airflow pass and serviceability. So that means we can pack these in a bit tighter than traditional. And I mentioned that line sizes are relatively smaller compared to, let's say, a low pressure refrigerant. Might be a factor of 7 times smaller line sizes as well. Compared to a 410A, it's about half the size.
Right. And compared to a chiller or a heat recovery chiller of the same rough tonnage, can you kind of compare what the footprint difference is for those
Let's
two?
take a low pressure centrifugal double barrel chiller versus what we're proposing here. I mean, it might be a factor of about half to a third the size.
Great, thank you. Let's see, still got lots of questions in here. I see one from about what type size of building will these work for, which we touched upon a little bit. So I would encourage you to take a look at we have a use case summary in our industry guidance package that kind of walks through those 4 different use cases. So LA, San Francisco, Sacramento, and San Diego. And that's for about 175 to 200,000 square foot buildings, large commercial office buildings. So you can kind of see what the modeled performance, energy use, and cost savings are for that size of building. And then, Sean, I don't know if you want to like kind of reiterate what you mentioned earlier about some of the other applications. We'll also have some information to come about our new multifamily project that will be the same technology.
Reiterating applications, everyone's unique. But this gives you a very strong toolkit to meet a lot of the challenges for each of those buildings. And that's why we got DMG here with us today. They are experts at finding the correct path and how to specify the equipment and make sure it works for your applications. And so that would be your first touch point for all of these. Reach out to them directly. And or otherwise you can reach out to us here at Flow, but I would pivot you towards DMG first. Isaac?
Yeah, I think the Flex Lab and our training lab testing are 2 smaller units that have been tested. There's much larger units that have already been installed around the country at different sites, commercial office buildings, airports, training centers. Uh, Sean, you you know the list, but there's a wide range of buildings that they have been deployed on and are being specified or designed into right now. And each one of those buildings is going to have some different needs. Some buildings, like if we get into hospitality, they have really high domestic hot water loads compared to almost no domestic hot water needs on a
Yeah.
typical office building. So that's why we want to talk to you about. That's why we've got these guidance, we've got these great tools that are out there. But yeah, we want to talk to you about your project. You may have a building with some really unique needs. We're doing some spaces that have processes in them, and those are unique load profiles. So each building that we're looking at is gonna we're gonna need to identify what's going on in the building, what are we replacing, or what are we needing for that site. That's going to be the start of every discussion. So we could go into a fairly small building with a complex load profile. We could be in a very, very large building with maybe a couple machines instead of just a single, 120-ton machine. We might use a couple of chillers to accomplish the total load of that building.
Or full campuses on top of that.
Yeah,
So,
absolutely. And then the heating portion of this, whether we have cold water coming in from the street, like we talked about at FlexLab, 50, 60-degree water, or we're having fairly high temperature, 140-degree return from an existing air handler that we've tied into. The temperature range, the entering temperature range is highly dynamic, and so that's another thing that again is different than some of the other heat pumps out there that are either just doing domestic hot water heating or doing some lower temperature, domestic, just HVAC needs.
yeah, if I can add to that a little bit, I'm going through some of these questions and answers here. How is it different than others? I mean, every component is a little bit specialized in what they do. But what we can do here that's really different is the high temperature. We can do a lot of flow variability. While we're not always wanting to do secondary, or variable primary flow rates, we can handle a lot of those different load profiles. The other big thing with CO2 heat pumps in particular, if you ever pay attention to those coming out of Europe, is that they always struggle on return water temperature, or they need a high delta T, where we have a process now that we can solve that directly. We can get up to 140-degree return water. So if you got 160 supply, that's only a 20-degree delta T, or 150-degree hot water. That's a 10-degree delta T you can deal with, which is very different in CO2 systems today. And if we go air side, we can push that all the way up to 170. So we have projects, as mentioned, around the country, from being a winner in the Empire Technology Prize in New York to deployments since we started this program. We are making sure this happens and is successfully deployed around the country.
If I can add one more thing, there was also a question or a comment more about, aside from deployment, who's going to deploy it? It's the local technicians in the area that need to deploy it. And one of the concerns that was brought up from a question was, the support infrastructure strategies for overcoming the local shortage of HVAC technicians qualified to do the system. And with all innovative systems, there comes that challenge, right, of the lack of knowledge, just on a base level, right? So I think that's what we kind of addressed here, and we made sure to emphasize during our project. That was a huge highlight of what we wanted to do here, was that tech transfer, that knowledge transfer that the resource provides, and then also that ISA provides at DMG with the training center, just to provide that knowledge right now to prepare the local technicians, the local contractors, so that they have an understanding for when this becomes scalable.
Adam, if I could add to that, yeah, we're absolutely excited to host the guys that need to be up to speed on maintaining, servicing, installing these systems here in California. Yeah, we trained our techs in Minnesota, so back at Flow, they have been very much investing in training. I think hundreds of union pipe fitters, installers, service and maintenance contractors over the last 2 or 3 years. I don't know what that total count is up to, Sean, but I know I've sent a number of our local contractors back there. I've
Mhm.
sent the people that work for DMG service, our controls team, our technicians that do diagnostics and maintenance. We've seen a lot of people back to their facility because my facility is able to handle kind of the 101, and this is more of the advanced stuff. It can also be taught back in Minneapolis.
Yeah, I would add that we do have an innovation center here where we do classes between 20 and 30 people at a time. We're doing it on a quarterly basis. We are working with multiple union halls to train lots of different technicians. And I mean, I'm a service technician myself. That's where I started. Got into engineering because I didn't want to be up on a cold roof or a hot roof anymore. Um, Design equipment so you don't need to go up there. But with that, we make sure we design reliability and we design serviceability in everything that we do. So every system has a built-in measurement and verification suite, so you can see temperatures and superheats, and if anything's out of line, with many advanced diagnostics that tell you the alarms. So the technician can go up to a unit and know what's going on with it really quickly and easily. And they think that they're going to come across this big magical thing that's going to be so complicated and to take weeks to learn. By about 6 hours to a day into the training, like, oh, I can run this thing and fix it. It's just a couple of variable speed compressors and brazed plate heat exchangers and a really nice control platform that make it acceptable. And then to make it even better, we make sure we do factory acceptance testing on every single unit that ever ships. And so we have load cells that test against that, mimicked after what we did over at FLEXLAB, and we continue to build and expand upon this and making sure that these things work. And we have the uptime, we have the reliability, and we put that in your fingertips so that you can have it as well.
Awesome. Thanks, Sean. Um, I know that there were a few questions earlier that we addressed in the Q&A, but I wanted to bring up in case anyone else was curious and they missed that. But we had a few questions come up about defrost and one, how this system avoids defrost. And then there's another question in the Q&A talking about newer air source heat pumps are improving control strategies for defrost that show minimal energy loss and no system capacity loss. Do we have any more details on how we compared this or how we can compare this to our system and other systems?
Yeah, that's always the big question with air source heat pumps, isn't it? So the way we do defrost, we got a number of patents on this. So just putting that out there, there's not others doing the same thing we're doing. We basically, with a transcritical cycle, that CO2 needs to run at, meaning it's not really a gas or a liquid, it's kind of both at the same time. Think of it as a super dense gas. We use the heating that we have, but we can continue to extract energy out of it all the way down to the outside air set point. So let's say you're 120 degrees for your return water temperature, you're leaving to the unit. So you got 120 to, let's say, 40 when it's cold outside in the Bay Area. Now, that extra temperature can be reapplied and used to preheat the outside air evaporator. Kind of think of it like a electric resistance heater on a fancy hotel mirror where you're taking a hot shower and it stays frost-free, fog-free. That same concept done with refrigeration circuits enables us to preheat the outside air coming into the evaporator, so it's always above dew point, and it never condensates. When you don't condensate, you don't have frost. That makes it a truly defrost-free system, and that's a heat recovery process that we use then, which actually adds a net benefit to the system. We lower our gas core temps, and we raise our suction temperatures in the process. So it just becomes an even better system over and over again.
Perfect. Thanks, John. There's another question regarding whether this system's eligible for some specific tax incentives or rebates. I don't know, Sean, there's one in here about OBBA Section 48.
Yeah.
But I would say in general, I would encourage you to check out our funding and financing guide and the net present value, the NPV analysis, because both of those, in the NPV analysis, we call out a few incentives that are applicable to the system. And then in our funding and financing guide, there's some examples of opportunities that may apply to a CO2 heat pump system. So, Sean, I don't know if you have any specifics on that one, but
I would just say that tax incentives and funding in this day and age are a dynamic moving piece. Um, reach out and make sure you're working with a if you're going after a tax professional who specializes in this. Section 48 still qualifies for some geothermal and energy storage items. Those are still eligible from my understanding. But again, you got to have an energy model put to it, and you got to do a lot of preliminary engineering to make sure you qualify in advance. Um, Other California incentives, they go utility by utility. Situation and market by market. So what happens in LA is different than what happens in the Bay Area, which is different than what happens in the rest of the country or San Diego or wherever else we're looking at.
Right. And that's a good point, Sean, that so we have, as one of our resources, we have some currently available funding and financing opportunities, and we acknowledge that those will likely be out of date pretty quickly. So the funding and financing guide kind of goes with that, and it's some instructions on places to look for funding and financing opportunities, and then just kind of like some guidance on what to search for, and then some explanations of what different financing mechanisms are if you're going the financing route. So thanks for bringing that up. I don't know if you guys had any other questions you saw in the Q&A that you wanted to address. Again, I would encourage people to reach out if you have some specific questions, whether it's about a specific project or just want to get into the nitty-gritty of the technology. I would encourage you guys to reach
Hey,
out and set up a conversation.
hey, Carolyn, I saw one that I thought we could tackle pretty quickly, and
Yeah, let's do it.
it was a CO2 comparison to or competitor CO2 units that maybe are coming from Europe or something, and how this might differ. And the two things I have seen in my experience, a lot of heating only systems that are very much focused on boiler replacement, maybe in some very small capacities, and or are focused on domestic hot water, and they're doing a very high lift. So they're targeting higher temperatures, typically higher lift, and usually lower capacities than what the the flow system has been designed for. So that's one difference. The other difference would be a lot of commercial refrigeration and CO2 in Europe and now in the US, which is not what the current heating and cooling system that we're talking about is, but possibly something we would talk about in the future. But the two kinds of CO2 systems, or maybe three, we see, Sean, what some district heating options too, really very different each one of those is a different application, a different temperature zone, or a different capacity range. So when this product came to market, it was targeting commercial HVAC, and sizing it for those buildings and designing a system that could be a high lift or low lift heating realm, not just one thing. So I think that's a broad stroke comparison to what we've seen, Sean.
Yeah, I would say you're right. Most of them optimize around condensing temperature, so they don't want to go to that transcritical mode. And that's where we leaned into that and truly embraced it and optimized all the controls and the designs and what we're doing to live in that mode most of the time, which is very different than other systems that try and get out of that mode, no matter the cost. I do see another one here about variable primary flow versus primary secondary and recommending application diagrams and designs and buffer tanks and minimum flow volumes. So there are a lot of systems that require a lot of system volume to account for controls and variability. And that's because they try to control on the water side of the equation rather than the refrigerant side. So a lot like VRF controls variable refrigerant flow internally. Our systems do the same kind of thing. And think of it VRF for water. So we can handle a lot more variability than other systems can. So that means instead of having 40 gallons per ton of refrigerant of system volume, you might be able to cut that down to 3. So that is a pretty huge substantial difference on hydraulic separators and buffer tank sizing and all that. for a lot of these heat pumps that require that huge system volume, you're putting a swimming pool's worth of water as a buffer tank on large system. Now we can get down to something much more manageable and feasible. So you can put this design into a lot more applications. As far as recommended application drawings, there are so many different applications, and we're happy to help you with recommended designs once we know what your goals of a project are.
Lovely. Thanks, John. So I know we're getting close to time. So I wanted to, if there are any last questions coming through, I think we could probably take one more. If not, Adam, any closing remarks that you want to make? I think maybe we
Yeah,
can, I'm gonna pull up the slide with the QR code.
yeah,
So
absolutely. I think that what we did here was a great achievement from everybody. I just want to thank the panelists for all of their work. From the guidance package to the testing of the unit. It wasn't just one isolated group doing one of these things. It was a group effort, and I think that should provide a translation to everybody else looking to implement this technology. Is that it can't take one group over another to implement it. It requires everybody to do their part in order to make any project for the CO2 technology as successful as possible. So I hope that, I think we were a great example of that. And I'm very proud to be sharing this information to you. And I'm hoping that we did something to help all of you today to educate and to spread awareness and to show that, from this demonstration that this is a great option to have in the HVAC industry.
beautifully said. I agree. Also, I'll just note on our resources, this is the first time that we're putting something like this out, and so we would love to hear your feedback on it. We want it to be the most useful and practical guidance that it can be. So yeah, it's posted on our website. There are a few resources that are going to be posted in the days to come. But yeah, I would encourage you, if you are looking through anything and you have feedback or any ways that you think those can be improved, we would love to hear it, and we value your input. So yeah, thank you to everyone that attended. I hope everybody has a great rest of their week. Enjoy St. Patrick's Day. And hopefully some people will get in touch and we'll chat with you soon.
Thanks, everybody.
Thank you.
Thank you.
Thanks.